Okay, so the most basic type of SR latch or set reset latch is called the NAND gate latch. Here, set and reset values. So the values that go into this latch, you have Q and then the inverse of Q comes out, but the values that go in for set and reset are normally high. So if you do nothing to this latch, they're going to be putting a 1 in. So in this case, it's kind of counterintuitive, but you must push one of these values to low in order to set or reset. So if I turn at set to low, then I'll set the latch and get a Q equals 1. If I turn reset to low, then I will reset the latch, and resetting the latch means Q equals 0. So that's how the NAND gate latch works. Okay, that's only specific to the NAND gate latch. So it's a specific type of latch, and you have to know how it operates. So this is what the latch looks like. And this is a feedback element that I was talking about. This is why there is memory. There is memory because the output from one of the NAND gates gets fed into the input of the other one. And that, in effect, holds a value. And we really need to walk through it in detail so that you can see why it does that. So this is our NAND, our SR NAND gate latch. Here's how it behaves. If S is 1 and R is 1, then nothing's going to happen. It's going to be the same as it was during its last input. Then if you drive S to 0, you set the latch. Q goes to 1. If you drive, and this is right here in the truth table. Now, if I drive reset to 0, then I have reset the latch, which means Q equals 0. By definition, means that it's reset. And if I put a 0 in set and reset, then I'm just being silly, and the result is invalid, and it does nothing reasonable. So just don't do that. You should never have this case. You won't have this case in reality. All right, so it takes quite a lot of effort to understand why this happens. So I've left quite a lot of space to do that. So again, we're looking at the NAND gate latch. And it's an SR latch. And the NAND gate latch, let's redraw it. It looks like this. So we have two NAND gates. We have set going into one, reset into the other. Q comes out, and then Q, the inverse of that same signal. So it's going to be sort of the opposite signal. And then there's a feedback from Q into reset, and there's a feedback from the inverse of Q into set. So those are your feedback elements that provide your memory. And in a NAND gate latch, we have to remember that, well, in any latch, we have to remember that S equals set and R equals reset. We should also remember that in a NAND gate latch, that these are both normally high. Therefore, you must drive them low. What does it mean in the real world to drive them low? It means give them signal of 0. So it means take the voltage away. It means open a switch or unplug a wire. So they have to be driven to 0 because they're normally sitting high. And we also need to memorize the truth table for an SR latch. Truth table looks like this. S and R and output. Output refers to Q. And when S and R is both 1, then this is the no change condition or hold. It means the output's going to be whatever it was before. And then in order to set, you must drive S to low. So this is what it means to set. And then if I want to reset, remember what set means Q equals 1. And reset means Q equals 0. That's what it means in every latch. Q equals 1 means reset on a latch, on any latch. In order to reset it, you need to drive reset to low. So you need to open a switch on reset or pull a wire on reset. And then there is this case where if you give it 2 zeros, then you're being silly. It's invalid. And so here, when you go and drive S low to set that latch, R just is still at 1. When you drive R low to reset the latch, S is still at 1. So that's what the truth table looks like. So let's look at the cases. So case 1 is when I'm going to let S equals R equals 1. So let set equals reset equals 1. So the result is the two outputs depend on previous inputs. So what you get here depends on what you had before. So let's just walk through. We're going to walk through every case in the truth table. Okay, we're walking through this first case now. So these are NAND gates. And Q comes out. The inverse of Q is there. And you should be able to draw this from your memory. Draw what an SR NAND gate latch looks like. So in these cases, I want to, in this case, I want to give an R here and an R here. All right, so what we need to do is remember what a NAND gate acts like. So NAND truth table. What does a NAND truth table look like? Well, we have S, R, or if we have two inputs, right? Well, let's just go inputs A, B, and NAND. So let's just remember what our truth table looks like, please. So an AND gate truth table says that the result is 1 only if both inputs are 1. And a NAND is exactly the inverse of that. So this is the result. This is the result of it, of each of these NAND gates. So that's important to remember. So now let's say we have this 1 is going into the NAND gate. So one of the outputs is a 1. That means we're acting here or here on the truth table. And then it depends on what the other input is, whether it's a 1 or a 0. It depends on what you're going to get out here. So if this input is, say, a 1, if it depends on its previous input. So let's say if that's a 1, then the result of this NAND would be a 0. And then this 0 comes through here, and we have a 0 and a 1. So the output would be a 1, and that 1 is fed back. So it depends on the previous outputs. So, or if the opposite was true, then the answer would be, this is our Q, and this is our Q bar, then the answer would be a 1 and a 0. So let's not worry too much about that, but that case is called hold, and it relies on what the previous case was. So now let's do the next step on the truth table, and let S equals 1. No, let S equals 0, because I need to drive it low, to set the latch. So S equals 0, and I'm setting the latch. So setting the latch case. It's this case here. All right, so we want to drive S equals 0, or give it a low value, unplug it or open a switch, then Q should go to 1, right? It should go high because I'm setting the latch, and by definition, setting a latch means that the output Q goes high. So let's draw that again. Again, we should know how to draw this. We should know how to draw a latch from memory. And then remember that the output of one goes into the input of the other. So there's our gate. So what we had is we already had a 1 here. And instead of a 1, we're going to momentarily drive set to 0. We are going to momentarily set this to 0. So in order to do that, so what that, if I were to do a timing diagram between 0 and 1, it was a 1. I'm going to momentarily set it to 0. And then I can switch it back if I want to, because there's a memory element. So at time t0, I set it to 0 in order to set this latch. And then I can put it back at time t1 if I want to. And so what that's going to do is it's going to put it's going to put a 0 through here, and that is, it depends on the state it started at. So depends on how Q started. So if the latch started at Q equals 0, so it was not set, then I have a 0 here, and I have a 1 here, of course, because it needs to be the inverse. So then that means a 1 came in here, and through a NAND gate, when there's a 0 and a 1, that's this case. So the NAND gate will then change. 0 and a 1, the output is going to be a 1. So we have set Q equals 1. Makes us happy because we drove S low in order to set that latch. Now that's a 1, so now a 1 comes in here, and the output of a NAND gate where 2 inputs are 1 becomes a 0. So we have reset the latch. Or sorry, we have set the latch. And what does that look like for Q? If I were to do a timing diagram, then it was at 0 and it turned to 1 and it stays at 1. So this is time t0, the same t0 that exists over here. And this is time t1 and it stays set. This is the signal Q. And similarly, the signal Q bar is going to be the opposite. It was high and it changes to low. So it stays unset. All right. That's if the latch started at Q equals 0. And now do if the latch started at Q equals 1, can I still set this latch by driving S to 0? Well, let's draw it again. What if it starts at Q equals 1? That's what it started at. Set, reset. You have the output and the output. Now it started at Q equals 1. I said that by definition in this sequence here, I am setting S equal to 0 in order to set the latch. So now I have a 0 there, and reset is still a 1. So let's see what's going to happen in this case. In this case, I have a 1 and a 1 here. And when a 1 and a 1 goes through, I look at my truth table here, then I get a 0. And then this 0 is going to come up here. And when I get a 0 input from a NAND gate, I get a 1. So therefore, driving S equals 0 does set the latch, which means Q went to 1, even if Q was already at 1. So in this case, just to summarize here, this case, I wanted to set the latch, so I drove S to 0 because it's a NAND gate latch. And even when Q started at 0, it turned to 1. And when Q started at 1, it turns to 1. So now we are going to do the next case in the truth table, which is resetting the latch. When we reset the latch, it means we want to drive R to 0, because that's what we do to reset the latch, and make that'll make Q go to 0, which means reset. That latch will get reset if we do that. So we need to pulse R to low. All right, so if R is already on high, then we need to pulse it to low. And then we can pulse it back up if we want to, but we want to just turn that signal low. All right. So let's draw our NAND gate latch again. And in this case, set is sitting at 1, and I want to pulse this guy low. He was at 1, pulse it down to 0 in order, because I know that if I pulse that down to 0, I'm going to reset that latch, which means Q equals 0. So it depends on the previous value, but let's say previously Q is at Q equals 1. So we already set that latch. So it's sitting here at 1. So then the input here is 1 and a 0 through a NAND gate from up here, a 1 and a 0 through a NAND gate will give me a 1. It'll give me a 1 as the output here. And then that 1 is going to feed back and have a 1 here, and a 1 and a 1 through a NAND gate is going to give me a 0. So this value turns to a 0. So what we've done is we made now Q equals 0. So the latch got reset. And you can do this again if you want to by starting with a 0 here. If Q is already at 0, so it's already reset, then when you drive R down to 0 to reset it, it stays reset. And then let's do the last case. So you can go through that on your own if you want. Let's do the last case. Oops. Simultaneous setting and resetting. So if you simultaneously set and reset, then that means you want S equals 0 and reset equals 0. It means, hi, I want to set this latch and I also want to reset this latch. Then what you get is very silly. So let's say you give a 0 here and a 0 here. So you're driving that signal low here and here. Then what you're going to end up with is a 1 and a 1. And this should be a problem. You can't have Q equals 1 and Q bar equals 1. Why not? Because Q bar is the inverse of Q. So they must be opposite from one another. Invalid. All right, so that's a walkthrough of why you get each of the lines of the truth table in a NAND gate SR latch.